Let me check to see for understanding about the motion and propagation of light waves. Ask you a question. What travels faster, radio waves or X-rays? Of course, you probably know that's a bogus question, right? Radio waves, X-rays, gamma rays, visible light, they all represent radiation that's a combination of oscillating electric fields and magnetic fields that oscillate together in time in planes that are 90 degrees apart from one another. So as time goes by, if you go farther down the line, the electric field gets a little smaller still, and smaller and reaches zero. And the electric field farther down the line increases in the other direction, and then decreases back to zero, and then increases some more. And if I trace all this out, I just get a sine wave. Well, at the same time the electric field is shrinking, its corresponding magnetic field shrinks, and they both reach their zero at the same point in time. When the electric field reverses direction, so does the magnetic field, at all points in time remaining perpendicular. Maybe a little harder to draw, but something like this, okay? But the propagation, well, it's in the direction of the electric field crossed into the magnetic field. So you can verify this with the right-hand rule. The speed is represented as a vector pointing to the right, and the value of that speed, at least in a vacuum, is very nearly 3 times 10 to the 8th meters per second, regardless of the type of radiation. So radio waves, microwaves, infrared, ultraviolet, and all types of light travel with the exact same speed. So what distinguishes any one from another? Well, really we can distinguish them in terms of wavelength and frequency. So looking at the way these are named going from left to right, we've listed out the types of radiation in terms of increasing wavelength. So you can see we're showing short wavelengths here in the gamma and X-ray part of the spectrum, and then we see the longest wavelengths here in the radio part of the spectrum. But we can break the radio spectrum into 2 parts and call it short wave radio and long wave radio. This presentation of the electromagnetic spectrum gives us even more information. It tells us whether or not the type of radiation penetrates the atmosphere. So in some cases it's a definite yes or no. In other cases it's kind of a gray area. So for example, microwaves do not penetrate the atmosphere. The atmosphere is opaque to microwave. However, the atmosphere is transparent to radio waves, and it's also transparent to visible light. So a lot of the other parts of the electromagnetic spectrum do not penetrate through our atmosphere. And so we can see here, get an appreciation for wavelengths in terms of other objects we're familiar with. So the wavelength for, now in this case we're listing in opposite direction, right? This presentation of the spectrum shows increasing wavelength to the right. This one shows decreasing wavelength to the right. So the longest wavelength or lowest frequency radiation radio waves are shown on the left end of this, and the longest radio waves have wavelengths approaching 1,000 meters, like the size of buildings, and that's really long wave, really low frequency AM radio. As you go towards shorter wave and higher frequency, you get into the FM and even XM part of the spectrum, and the wavelengths in that case are roughly the same as the size of a person. In fact, the wavelength of, I believe it's, KLOS, I think, is the radio station that broadcasts at 95.5 megahertz. That's the frequency. That's the same as 95.5 times 10 to the 6th cycles per second. That's 9.55 times 10 to the 7th cycles per second. Well, there's an equation that relates speed, frequency, and wavelength. Actually, we should call it C since we're talking about light. So all waves, their speed is equal to the product of their frequency and wavelength. For light waves, we call this speed C. This means wavelength is equal to speed divided by frequency. So if you divide 3 times 10 to the 8th meters per second times 9.55 times 10 to the 7th cycles per second, then you get a certain number of meters per cycle, which is the wavelength. And in this case, it comes out, total coincidence, to be 3.14 meters, or in other words, pi meters. So KLOS is the only radio broadcast that gets the distinction of having a wavelength of pi meters. I actually once called in to their radio station. They put me on the air, and I tried to explain to them what a neat thing that was, but the DJs had no idea what I was talking about. The wavelength for microwaves is on the order of centimeters. This is why the cavity in your microwave oven is only a few centimeters wide and centimeters deep. Infrared radiation has an even shorter wavelength, and so on. Visible light has wavelengths on average of about half of a micron. So 10 to the negative 6 meters is called a micron. And 0.5 micron is the same thing as 500 times 10 to the negative 9th nanometers. Or I'm sorry, 500 times 10 to the negative 9th meters, which is the same thing as 500 nanometers. That's near the middle of the spectrum. The visible light represents the smallest fraction of the electromagnetic spectrum, and it corresponds to wavelengths that range at most 700 nanometers and at least 400 nanometers. So 700 nanometer wavelength is the longer wavelengths, and that's the wavelength for red light. 400 nanometers is the shortest wavelength, highest frequency of visible light, and that corresponds to violet light. So any wavelength shorter than that of violet light is called what? Yeah, ultraviolet, right? Frequencies any greater than the frequency of violet light are ultraviolet, and in the same regard, frequencies lower than that of red light are infrared. The rods and cones in our eyes do not respond to those frequencies, and so we can't see them, but they're light nonetheless. So moving to the right, wavelengths get smaller and smaller. The wavelength of X-ray radiation is roughly the diameter of an atom, and the wavelengths of gamma radiation is roughly the diameter of a large nucleus. So when we talk about the electromagnetic spectrum, that's what we're referring to, is all the different types of light waves. They all travel with the same speed as one another, and in general, as the wavelength goes up, the frequency goes down.